Okay, so I think we can start. Yes? So happy to welcome you on behalf of the Tech, Talent and Methodology teams. Since last year, we worked a lot regarding this continuous learning mindset because we truly think that it's important to learn. Why it's important to learn? Because it's a way to have critical thinking, have some ideas, innovation, expertise, even watch technology watch. But we are super lucky because here at Swissquote, we have budget for learning, training. It's super easy. But sometimes I think that it's really important to have the conference coming to us. So that's why we are doing this kind of event for you. So today, we are lucky to receive Yoan Thirion, an agile coach, a technical agile coach even. He's going to explain his life, so I'm sure. So welcome to the speaker, and I'm sure that he's the first of a long series. Thank you.
Thank
you.
You
can applause. Hey.
Thank you, Edwidge, for the introduction. Thank you, everyone, to be here today. Yeah, no problem. I'm here to talk about clean code for today, but not the usual way of talking about clean code. We'll talk about it from the cognitive point of view. And we'll see what is clean code and what do we mean by cognitive or cognition. Before I start, I just wanted to introduce myself. I'm Yoan Thirion, just like Edwidge said. I work for a company called Pixie Swiss. I work as an agile technical coach. Basically, my day-to-day job is I try to help as much as I can development teams to deliver in a more efficient way, or as efficient as possible. I work on the technical side, on techniques like TDD. I teach some practices like TDD, everything related to quality and testing. And I try to help on communication at the communication level, like an agile coach, and the process level, and so on. If you want to deep dive into this topic of technical coaching or craft coaching, we can talk at the end of the session. One last word about me. Sorry for my bad English. I'm not used to talk in English anymore. So yeah, sorry for that. I'm French, so. What is my intent with our talk today? What I want to push with this talk is really help everyone understand how our brains work. That's why we'll experiment some limits of our brain during the session. What I wanted to achieve as well is really share with you techniques and practices that can really help us as developers to be better at two things. Read code and write code. So, in the title of the conference, there are two things: clean code first. Who has already heard about this term, clean code? Raise your hand. Yeah, maybe 50% or something like this. And who has already read the book from Uncle Bob? Yeah, some of you. Okay, cool. So clean code, it's a book with plenty of concepts, plenty of guidelines, let's say it like this, written by this guy, Uncle Bob, in something like, I think it has been published at the end in 2008 or something like this. So it's not that new. Huh? It's not that new. The idea in clean code from Uncle Bob was really to write, okay, what could be the principles that could guide us as developers? What can be the rules that can help us to write maintainable code? And by maintainable code, we mean understandable and readable for a human being. So, two stuff in the title. One part, clean code, and the other part, cognition. I let you read the definition of cognition because I don't want to read it. I'm a little bit lazy. Yeah, it's a Wikipedia definition. Okay, you have the time to read it. Basically, what I would like for you to remain is you can see cognition as the process of thinking. We can see it like this. Let's keep it in mind. What I will demonstrate during the talk will be a lot of principles coming from this book and coming from a lot of scientific studies made around the world. For the book, what I will mention here, it has been written by Dr. Felienne Hermans. She is a professor at the Leiden Institute of Advanced Computer Science in the Netherlands. And it's pretty much here. Ah, ok. Ok, c'est mieux comme ça? Ok, it's better, yeah. Sorry for the noise. Okay, I try to keep it like this. So there will be two aspects in this presentation. At one side, we will see how we can be better at reading code and how we can be better at writing code. And before we see some techniques, some principles, some guidelines, I wanted to test your brain. That's why you need a pen and you need a block note. I will ask you to make a small experiment. I will... yeah, sorry for the technical aspect. So we will test your brain. The idea is really to take a look at the following program. So I will show you a program for 3 minutes, and you will have to reproduce it at the end of the timeline. At the end of the time. So you don't. I need to stay here, I think. Yeah. Okay. So you will look at the program for 3 minutes. Don't reproduce it on your paper during the 3 minutes. You will reproduce it after those 3 minutes. So you have 3 minutes to try to remember as much as you can from this code. I don't move. I didn't move. It's not me. Okay, let's try it. So 3 minutes, you take a look at the code, and then you reproduce it on your paper. Okay? Civil have 1 minute.
Okay, time's up. You need to reproduce. I ask you to reproduce, please, as much as you can, this code. I try to do it individually. I know it's hard. Let's take 1 minute to finish. Je sais pas si c'est passé. Still time. Okay, let's break here. I can see differences. Who is really proud of his or her reproduction performance? No? Yeah? Please, you can come here and stick your paper here. And who is really not proud of it? The others? Yeah, you can come here as well and put your paper here, please. Just to compare. Yeah, you need to put it. Yeah, let's do it like this. Yep. Thank you. Okay. Yeah, it's not that bad at all. Okay. It's pretty good. I've done it multiple times, and honestly, it's really good. Even for the one who are not proud, who was not proud. So, yeah, it's not perfect, that's for sure. Yeah, I don't think anyone could have the array initialization. You have all the numbers? Anyone has all the numbers from the array? No? Yeah, it's almost impossible. Well, it's really impossible. We will see why in a few minutes. Thank you for that. Thank you for having done this experiment. We'll debrief it in a few minutes. So, what happens in terms of cognition when we leave at the end? We have a lot of information coming in our mind continuously. What happens is those informations come into our filters. We won't go into what are those filters. There are plenty of them. But basically, those filters are really here to help us to focus on something. Otherwise, we would think about anything. Oh, there is a jacket. What this jacket is here? And so on and so on. don't want to have this kind of thinking all the time. So the information is filtered. Then it comes to what we call our short-term memory. You can see it as a RAM, a cache for our brain. Because it's a RAM, our short-term memory is limited. We have a limitation and a strong limitation regarding our short-term memory in terms of time, but also in terms of slots, the number of slots available. Regarding the studies, it's between 3 slots, and we'll see what is a slot, 3 slots to 12 slots. That's why, it was really hard to remember all the numbers from the array, for example. So, some information are stored in our short-term memory when we think about something, when we want to remind something, or we want to think about something, and then the information in our short-term memory is processed by what we call the working memory. It's basically our processor. It's where the thinking, the process what we call thinking, is actually happening. So it's really our processor, the working memory. And then we have something really important, our hard drive, the long-term memory. Here, in the long-term memory, we can store memories, we can store information for our entire life. If under certain conditions, for sure. So, if we recap, information comes to our filter, it comes to our short-term memory in where we can store some data, maximum 12 information, 12 slots for a given period of time, 30 seconds. Information is processed by what we call our working memory, and we retrieve some data to process the information in our working memory from our long-term memory, just like a computer. What happens when we read code? What happened to you a few minutes ago? So you use your short-term memory to try to store as much as you can information regarding the code. The array, the number of for loops, the if, I don't know what was inside your short-term memory at the time. Yeah, maybe remind the name of the class, for example. You use your long-term memory to retrieve the knowledge regarding the algorithm. You had a good indication with the name of the class, insertion sort. You retrieved some over data, I think. Everyone is a Java developer or have a Java background here? Yeah? So it was pretty evident that it was in Java, so you didn't have to remember, okay, it's a program. You have maybe stored only one information, it's a program, so you didn't have to say, okay, there is a public static void main method that takes as an argument a string of an array of string that called args and so on and so on. So it was easier for you to let's say, reproduce the code, and you use your work. Here you didn't use your working memory, but when we read code, we use our working memory to try to understand what is going on regarding variables, regarding the program itself, in terms of decision making. This process is called tracing. When we debug, we have this kind of stuff made by the machine. When we do it in our brain, it's called tracing. So we mentally execute the code to try to understand it. Basically, you did it. You stored maybe two loops, a boucle, it's in French. You stored maybe the name of some arguments. And what was really interesting, and it's not really visible here because even the worst case was really good. Here, the exercise was really here to make you touch the limit of your brain, the limit of your short-term memory at least, and maybe the limit of your long-term memory. You have all Java knowledge, and if we have done it with, I don't know, business people, we would have a different let's say, level of exigence regarding the result. But the more information you have in your long-term memory regarding a topic, the better you can reproduce the code, and the better you can understand the code. So, how can we improve us as developers regarding cognition? We know we have limits. We have touch one, short-term memory. We cannot store for other information in our short-term memory. So how can we improve on reading code? But the first question, it's a good one, why reading is so important in development? There are plenty of research regarding the topic. This one, let's say, it's a consensus. It's a scientific consensus. Yeah, I show the screen, but the screen is not here, it's here. This one is a consensus. So there is, we can say that we spend, as developers, almost 60% of our time reading code. It has been calculated, it has been proven by science, by multiple studies. So it's the lowest number that you can find on the internet. Sometimes you can read from Uncle Bob studies at his level, let's say it like this. He will say it's 90% of your time that you spend reading code. It's not really scientific, it's just an opinion, but why we read code? We read code for various reasons. When we want to add a new feature, when we want to debug, when we want to understand a system. So if we can improve how quickly we can read code, we can be really better and really more efficient as a programmer. If we can improve those 60% of our time. If we take a look at this, we can see that we have limitation in our short-term memory. So when we read code, if I read a method with 50 lines of code, for example, that's for sure that at one point, my short-term memory will be, I will be out of short-term memory, let's say it like this. I will have an out-of-memory exception in my brain, that's for sure. Because there is a time limitation, 30 seconds, and there is a size limitation from 5 to 9 regarding given studies. For others, it can be less than that. In terms of slot, and we will identify what is a slot in a few seconds. So we have definitely a memory issue when we read code. Imagine you have 7 parameters in a method. You read the 7 parameters of this method. When you go one line below, you don't have space remaining in your short-term memory. So you need to find space and so on and so on. So how we can fight this size limitation? Well, there is an experiment that has been made in the 40s by a guy named De Groot. I don't know who has already heard about this experiment? De Groot chess experiment? Yes? Yeah, cool. Basically, what De Groot wanted to prove, wanted to study, it was really the impact of memory on intelligence. It was a time in which researchers wanted to deep dive into the brain, to deep dive into the mechanism behind the brain, behind our thought. So he made a small experiment with expert players, chess expert players, and chess average players. What he has done is he set up a chessboard, like a normal game, and he shows to participants of the study this board for a given amount of time. And then the participant of the study had to reproduce the chessboard, just like you did with the Java code. What he discovered by doing it, and you can guess the result, but I think you have it all in mind. Expert players were really better than average players to reproduce a chessboard. It was really interesting. So at the time, he thought, okay, what makes an expert player an expert player is really his capacity to memorize stuff. To demonstrate it, or let's say to convince him that it was a good point of view, he made a second round of this experiment, in which he scrambled the chessboard. So every piece, every pawns were disposed in a random way. And what he has observed, average and expert players were performing the same, exactly the same. So why? He asked the questions, he tried to figure it out why. And what he has discovered at the time, he discovered one really interesting thing, that the experts grouped information in a logical way. Here, the chess experts, expert players, were grouping information into their chunk, into their slot in their memory. They didn't memorize, okay, there is a pawn, there is queen in a9 or something like this. They were just memorizing one information regarding the setup, for example. Okay, it's a Sicilian opening, for example. So, based on their previous knowledge on the chess, they memorized only one stuff on the chess, or one or two information. If there is a Sicilian opening, here it's a London one, and so on and so on. So this kind of information take only one slot in their short-term memory. That's why they were able to reproduce to perform really well when the game was a real one, and they performed the same when it was a scrambled one. So chunking, it's called the chunking theory, but he has proven at the time. What is really interesting, and I discovered it by reading and following Thirion Hermans, there are a lot of studies regarding computer science. So they did exactly the same experiment, but with programmers in the 80s. And they found exactly the same result. Regular programs, experts were performing, were really well performing, and when the programs were scrambled, exactly the same result than with the chess, performing almost the same. So, what is this mysterious thing than chunking? How we can apply it to our code? Chunking. I will ask you to take your paper once again to make a small experiment to discover what is chunking, and you will see how you can chunk information in your brain. Everyone is ready? So I will show you a sentence for 5 seconds. And you will have, just like earlier, you will have to reproduce it on your paper, okay? Let's start. Let's reproduce it. Yeah, 5 seconds, it's fast. At least one sample? Don't worry, nobody can do it. Are you ready for the second round? We'll do 3 rounds. Second one. Normally, you should perform better in this round than the previous one. Yeah, it should be easier, at least. It consists of letters that you recognized, I think. And what is interesting, in chunking one, in part 1 and part 2, there are exactly the same number of words, 2 words, with the same number of characters, 14, and the same number of different characters. And here, let's try to chunk, to group information in your short-term memory. One last time. Easier this one, eh? Here, what you have experimented with those 3 examples was really the mechanism of chunking. We group information into our short-term memory in slots. In the first round, it was almost impossible for anyone on Earth, I think, to remember this in 5 seconds. It's really, really hard. You don't know the characters, so you need to, for one character, you need to say, okay, there is a circle with a dot inside it, and so on and so on. So almost impossible. In the second round, you had the opportunity to say, okay, there is an X, a Q, an L, 2X, and so on. So it takes less slots in your short-term memory. And in the last round, you were really able to group information in something logical. Yeah, 2 words, Swissquote, 2024. Like the chess experts, you did exactly the same at the last round, at least. Yeah. Okay, now that we know that if we can chunk information, we can remember stuff, and we can really perform on this kind of exercise and in our day-to-day work when we read code. So how we can be able to write chunkable code? And what do we mean by chunkable code? Yeah, first thing, you are allowed to disagree, but a good way to chunk information in code is to use patterns. Here it's OP patterns, or object-oriented programming patterns, but you can use others depending on the paradigm. But the idea with design pattern is really be able to chunk information. If I see at one point, I don't know, a facade on something, I don't have to deep dive into the facade to understand what's going on. I see it's a facade, okay, it's a facade on something, and I don't need to deep dive into it. So it's a way to group information in our code. Here it's a small example of it. Imagine this code process in which you pass a payment strategy. If you have, instead of at line 9, a huge switch case or huge if-else with, I don't know, 1,000 lines of code, you would have to deep dive into the code to understand what's going on. Here you don't care about what is the strategy behind it. You pass a strategy, you group information, it's a payment strategy, no matter what is behind, a credit card, an eBay or whatever, Bitcoin or I don't know, you don't care about it. So it's a really efficient way to chunk data, to chunk information in our code. It's not new at all, but it can be really efficient. Another way to be able to chunk information in our code is to write commands. But I've seen in clean code that every piece of code should be self-explainable. Yeah, that's for sure. There are different kinds of commands in code that you can use in code. There are high-level commands and low-level commands. And I want just to take a few seconds to make the distinction. So one efficient way to chunk huge piece of code can be to use commands. Because in the commands, we can understand a module, for example. Here, I don't know anything about the code base. You will be able to take a look at it. I will send you the slides after it. I don't know anything about this module. It's written in Clojure. I'm not a Clojure developer, but I want to understand what's going on. Okay, I just have to read the small description of the module to understand what's going on, to understand what is behind the notion of churn. So it can really trigger my long-term memory. These commands can trigger really my long-term memory. Okay, churn, it says code churn is related to the quality of modules. The higher the churn, the most post-release defects. So it makes echo to my source control, and so on and so on. So I can really relate and understand what's going on just by reading a few lines of commands. High-level commands can really help us to chunk huge piece of information, huge piece of code, classes, modules, projects. Low-level can be a burden for our brain and can be a burden for the chunking process. Sorry in advance if you have this kind of rules, but I need to say it. I have seen a lot of companies using this kind of guidelines. Every piece of code should be documented. Every piece of code should be should contain the command. So for one line of code, you have a command, a useless command. First line, the exchange rate are stored in the map. Yeah, it's the definition of the line. Private constructor, yeah, I can see it. It's a private constructor. It's beautiful. It's not callable from the outside. Yeah, it's the definition of private constructor. We don't care about this kind of command. It's really the kind of stuff that really create noise in our code and yeah, makes it unreadable, unmaintainable, and so on. So high-level commands can really help us to understand code, chunk code. Low-level is really a burden. So here we have seen some techniques, let's say, to chunk code, to chunk piece of code, and I will make a small demo just after it with my slides. But how can we be better at reading complex code? Because yeah, we don't work in code in which we have only 10 lines of code or something like this. Well, regarding working memory, so it's really the process of thinking. Remember the process of tracing, of trying to understand the code, to try to deeply understand the code, what's going on in the code. You can see it as really the short-term memory applied to a problem. So we have a problem that we want to solve, and we use our working memory for that. But just like for the short-term memory, we have limitations. We are able, in our brain, to process 2 to 6 things at a time. So it can be really limited. It's a really hard limitation. In the context of working memory, this limitation or this capacity is called cognitive load. There are plenty of stuff now on the market or in the industry regarding what we call cognitive load. I invite you to read or I don't know if you already know it, but to take a look at what we call team topologies. It's really the purpose of the book to focus value stream teams on what we call cognitive load, or focus to help them to respect their own cognitive load. So it's everywhere, cognitive load, plenty of stuff regarding it. And when we read complex code, how can we be better regarding our working memory? So I will show you some techniques. The first one is refactoring. Refactor code to reduce cognitive load. And I will take an example. The idea here is to say, I have a complex code in front of me from my point of view, because the complexity, let's say, the level of complexity for one person is different for another. So for me, it's really hard to understand a piece of code. I can refactor it to replace what is unfamiliar for me with something familiar. So I take an example. I don't know if everyone is comfortable with this kind of data structure. Here I use a neighbor, I use a map, sum, double value, and so on and so on. So it's basically functors and monad. It can be scary when we say it like this, but it's really easy to understand. But it's not that easy when you don't know the principles behind it to understand this kind of piece of code. What do we mean by map? What is a neighbor? Why do we have this kind of map function, result, dot, from, and so on and so on. So what I can do when I see this kind of structure, I can refactor it to make it easier for me to understand. And I can use my IDE for that. It's really the purpose of my IDE. I have plenty of automated refactoring to help me better understand this kind of code. So, automated refactoring. I extract some variables, I extract some functions, so it's easier for me to understand. And at one point, when I have understood the piece of code, if it's a refactoring just to reduce my own cognitive load, I revert my changes. It was just to understand a complex piece of code for me. So what we need to understand as developers, and as human beings at the end, what is really easy for me to read or to understand really depends on my prior knowledge on the topic. Business knowledge and technical knowledge. So here I cannot impose to the rest of the team, okay, I don't want to use either, or I don't want to use map function anymore, I want to use for. No, if there is a convention, it's me. I have to train myself on this kind of topic. But for the purpose of understanding at one point, I can use this first technique to help me at one point, to understand this kind of structure. What we can use when we are working on complex code, it's really a school thing. We can annotate our code. We can annotate our variables to try to understand what's going on. Which variables have an impact on the process, on the flow. We did it, I think, at the university. We draw lines between the code, between the variables to understand, okay, which occurrences have which impact on what. And we can couple dependency graph with state table. It's the same kind of stuff that we have studied state table, it's basically we focus more on mutation, which lines or which line of I don't know. Well, yeah, each mutation we write one row, and in columns we put the variables to see what's going on. So it's a way to, let's say, reduce our cognitive load when we read code. Take some notes just to understand what's going on. It can really help us if we are in front of a complex piece of code. What is really interesting regarding science, there is a strong correlation between there is a strong correlation between reading text and reading code. It's the same areas of our brain that are stimulated. So the question that we can ask to ourselves, could we apply text reading strategies to reading complex code? What are the strategies when we read text? Well, the first stuff we learn at school, I think it was in high school, we start by activating. We have a text in philosophy, in geography, I don't know, we don't care about the I did. So we start by activate our previous learning. We actively think about things that could relate to the topic of the text. Then we monitor when we are at school. We monitor our understanding. Okay, I have understood this paragraph, I didn't understand those lines, and so on and so on. We try to determine what is important in the code or in the text here. What is important? So often in a text, it can be in newspapers, it can be in a book, you have only one part that is really important. So you need to figure out which one is. Inferring, try to find facts or to find other stuff that are not in the text, that can really relate and help you to deeper understand the topic. Visualizing, when I was at school, I was doing it a lot. Try to create a mind map to better understand what is the relations in the text, what is the impact of what, and so on and so on. Questioning, stuff that we do at school as well, asking questions to ourselves regarding the text. And summarizing, create a short summary of the text. It was really like this that we tried to understand text when we were at school. And when we are in front of a really hard to understand code, we can really apply it. We can apply this kind of strategies. Here, I have done it for the sake of the exercise. I have made a small example of it. Which kind of questions we can ask to ourselves regarding activating, for example. Sorry, it's in French. Activating. Which information stored in my long-term memory can help me to understand this code, for example? Okay, I see it's a pipeline class. There is the notion of project, notion of configuration, and so on and so on. So what are the connections I can do? What is the important part? I can really write it. Okay, this project run test, deploy, and so on. It seems important because we take decision here, and so on and so on. Questioning. Questioning is really something that we have to do, or what we must do when we debug code, for example, questioning ourselves. Take a step back to better understand what's going on. Just by asking ourselves questions can really help us to solve the problem. So if we debug, or if we want to better understand a complex code, it can really help us. Here, if I take the example of this pipeline, this famous pipeline, and it should remind you something, this kind of stuff. In this example, I have just made a screenshot of Sonar Cloud. There is basically a measurement of the complexity of this code. There is a high cognitive complexity, or it can be challenged, it's 19. It can seem low, but I don't think it's okay. And I can really apply what we have seen earlier. I try to chunk my code. And the better way to chunk your code to make it more readable for anyone, it's really easy. Use your IDE, extract method. extracting method is really the way to be a chunking master, to help your brain understand code, to help your colleagues understand code. By just extracting method, I don't touch anything else. I use my IDE, I safely extract methods. I can go from one piece of code that can be hard to understand because there is a high cyclomatic complexity or high cognitive complexity. I can go from this code at the left to the code at the right. In maybe 2 minutes, maybe 1 minute. And what is really cool or good with what we call functional programming, I can go further as well. I can really use the principles behind monads, functors, monoids, and so on, to write code that is really readable like a book. Here, well, like a book, I don't know, but readable at least, and understandable. When you know what is a flap map and so on, you can read it like this. Okay, there is a project, I run the test, I deploy, if there is an error, it's logged, unexpected or exception occurred, and that's it. 1 sec to understand it. It's really the purpose, or it's really one good point regarding functional programming, and you can use it in Java, you can use this kind of paradigm in object-oriented programming in Java, in C#, or I don't know which kind of languages you are using today. Chunking can really help us, and by chunking here I mean extracting methods. One other thing that can really help us as developers nowadays, AI. There are plenty of posts every day regarding AI. One really good thing about it, if I don't understand this kind of structure, this kind of data structure, either and so on, I just ask to my ChatGPT, CodeGPT, Cursor, or whatever, and I have an answer. Okay, this is a stream operation. It's not really a stream operation, but okay. It's not a stream in Java, it's using a Vavor library, but it's okay. But calculates the total cost of the order, it assumes that line is a collection of line order, and so on and so on. So I just use my assistant, and I can understand a piece of code that is really hard for me to understand in a few minutes. The feedback is really quick, but after you need to process it, you need to understand it. You need to understand the feedback of the AI. The only warning I can make about it, if you are interested in cognitive science or psychology or whatever, there are limitations of the intensive usage of this kind of tool. And there is one here, at least. There are others, but it's called the Google effect, or digital amnesia. The more you use this kind of tool, the more lazy your brain will be. It has been measured. It can be a little bit scary, say it like this. It's really our brain tend to forget information or to not retain information because it knows now, but we can access this information later on. Yeah, technology has a huge impact on us as human beings at the end. So we need to think, is it the kind of stuff that I want to automate, or is it the kind of stuff I want to retain, I want to integrate in my brain, in my long-term memory, that I can be able to reproduce and to use it on a daily basis. Okay. Or we can write better code. It won't be a surprise, but we need to be better at naming things, really better. Good names can really help our long-term memory to process information, to relate to stuff. So it can be really helpful to understand deeply a business. It can help us to really understand the technical side of our systems as well. There is a measure here, almost around 70%, 72% of our code are names. So names are everything in our code. So if we don't name it, if we name Amanda X42, for example, it can be really hard to understand what's going on. And I've seen it a lot of time in different companies. Names play a huge role in code reviews. There are a lot of ping-pongs in code reviews regarding the names. Because we don't agree on the naming, we don't agree with our business, we don't agree with inside the team, we don't agree inside the program, and so on and so on. And one last point, names are the more accessible documentation on the system, or the more up-to-date at least. There are plenty of other studies regarding naming. Some guys like Simon Butler have tried to define what is a good name syntactically speaking. Typically, if you have external underscores or stuff like this, it's really hard for our brain to process information, so it's the kind of stuff that you want to avoid in your programs. Code smells are proven. It is proven as well that long methods, a long list of parameters can be really hard for our brain to process regarding the limits we have talked earlier. So we try to avoid. I invite you to avoid this kind of stuff as much as you can. That's why it's really important to have feedback loops inside your team. Pair programming, it's an instant feedback loop. Pair programming regarding the code. You can have other kind of feedback loops, mob programming. You can have unit testing, automated tests, and so on and so on. But it's really important to have this kind of stuff and to detect also this kind of code smells like long method and so on with tools like Sonar Cloud, Sonar Cube, or whatever, Codana, and so on. Yeah, we'll skip this one. Regarding how we can write good code, let's say it like this. We need to be aware that names are really important, so we need to invest time on it. We need to avoid code smells. We need to write, to use names that are syntactically correct. And we need to avoid as much as we can what we call linguistic antipatterns. It's a work in progress study by Venera Arnaudova, in which she has tried to reference different antipatterns on our code, on code base in general. Not necessarily mine or yours. So we have seen that often there are methods in code that do more than they say, that's for sure. Something hidden in the code that is done, maybe send an event, or publish an event somewhere, or something like this. It's not that bad in this one, but it can be bad, bad in other case. Some methods that say more than they do. You have an example here. Methods that do the opposite than they say. Yeah, it can be really hard to read. It can be really hard to trust the code if you have this kind of anti-patterns in it. Or identifiers with names saying the opposite or saying something different but the entity containing it. So is valid that contains 42, for example. It can seem really trivial, but once you have numbers in mind, and I invite you to take a look at it, you can see with 7 open source projects, huge ones, you have 11% of setters in the code that also return a value. It can be a pattern. Maybe you want to chain stuff. Maybe you want to have this kind of stuff. But okay, you need maybe to deep dive in it because it's huge. 11%. 2.5% of method name and the corresponding command give opposite description of the working of the method. So don't rely on comments, on no-level comments at least. And the worst, 64% of identifiers starting with is or as are not Booleans. And I have seen it in a core business, in a core banking system. I won't say the name, but everything in the code was really smelled like this. You have void method that says get something. Void get something. What the fuck? You have is as that returns an integer. Wow. Okay. Okay, so how we can protect ourselves to this kind of stuff? I really invite you to consider to have checklists in your teams. It can seem silly, but it's really helpful when in teams you do code reviews to have checklists that says, okay, we don't want to have methods longer than 10 lines of code, for example. I don't know. It's a shitty reference, but this kind of stuff in it. Try to identify linguistic anti-patterns during your code reviews, stuff like this. What is really important, I think, to try to fight this kind of stuff, linguistic anti-patterns, code smell, and so on, it's really to align yourself as a team on what is a good piece of code, to make some code katas for it, to make some mob programming session, to align as a team what are our guidelines at the end. Yeah, I need to rush a little bit. I invite you also to take a look at ArcUnit. I will just show you. Who has already used ArcUnit? One, two people? Okay. Because we can automate detection of some linguistic anti-patterns. I don't say it's a silver bullet, but we can automate detection of the kind of stuff that we have seen earlier with this kind of tool. So ArcUnit is basically a library that can help us to automate tests on our code, on our production code. If I want to detect that an is method, a method starting with is not returning something different than a Boolean, I can write it. And it's basically a classic unit test behind it. So I have a feedback loop instantly on my computer. So it can be really helpful, and you can also check architecture rules. If you want to make some hexagonal architecture, to use hexagonal architecture, onion architecture, or so on, you can check some rules regarding your code. It is really powerful. And I had a discussion, so I know you have already this kind of tool, so tools like Sonar Cloud can really help us, Codana or other static code analysis platforms. But I invite you as well to, if you don't know the topic, to take a look at what we call behavioral code analysis. You can take a look at the work from the guy named Adam Tornil. It's really interesting. If you want to talk about it, we can talk about it at the end of the talk. I need to rush a little bit, sorry for that. So, I wanted just to finish the talk with a little abstract. So we have code smell at one point in our daily basis when we work on code. Yeah, it's not always what we want to see in code base. So we need to deal with it. We can see some linguistic anti-pattern and so on, but we need to think about, okay, how we can improve this kind of code. How we can continuously refactor our code to preserve our cognitive load when we read code, when we maintain code, when we try to understand code. So we need to think about chunking, how we can make our code more chunkable for anyone. So we can use patterns, we can use better naming, we can use high-level commands, we can use extract methods, refactoring techniques, like Mikado, like a lot of stuff. And we can automate what we call LAP detection, so linguistic anti-patterns detection, really. It's a good investment. So, from my point of view, the work of Felien-Hermans, that is a science vulgarization of a lot of studies around the world, it's not really new. It's really a scientific endorsement of the feeling that we have in our code. I see it like this. What is clean code is now proven by science at the end. What makes a code readable for a human being, small methods, good names, and so on and so on. So it's really clean code, an endorsement for clean code. Because we need to remind one thing. The code at the left and the code at the right, in this example, are doing exactly the same from the business point of view. From the human perspective, are you able to read the code and maintain the code at the right? I don't think so. To understand what's going on here, it's really shitty. Yeah, and there is some brain fuck in here. I don't know if you know brain fuck. There is a comment in brain fuck. So we need to really remember on a daily basis, okay, we write code for humans, not machines. A machine, a computer, our compiler, at the left or at the right, there is no good or bad answer. There is no good or bad code. There is much more to say regarding programmer's brain, and I invite you to take a look at the book or to take a look at the infographic I've made regarding the book. There are other stuff regarding what we call long-term memory, how we can improve our long-term memory, because it's really the way we learn that can impact the way we read, the way we code, and so on. or we can better handle interruptions or onboarding new developer in the team, and so on and so on. Small advertisement. Yeah, I'm a huge fan of everything related to craftsmanship. DDD, TDD, ATDD, BDD, every stuff in DD. And with a friend, we have created what we call the Advent of Craft. It was for last year, but during 1 month, we have published one challenge with the solution on the next day. So if you want to learn stuff regarding TDD, or if you want to have some code katas, you have one code kata per day with a solution with, let's say, the difficulty increasing every day. So at the end, maybe you will spend 2 hours or 4 hours to refactor the code or to understand the principle behind it. So we have covered a lot of stuff. If you want to deep dive into functional programming in Java, C# or whatever, we used a lot of libraries. We have covered Java, C#, Kotlin, and TypeScript. And Scala will come in a few days. I organize a webinar in French. It's totally free. Devenir un dev encore plus agile, in which I will talk about craft practices as well, property-based testing, everything related to testing, and refactoring as well. And I organize a training in April in Geneva. If you want, you will have a link if you are interested in this kind of stuff. And I will be with Edwige and Laetitia at DevOps Geneva in May. It's in May. Yeah, thank you. Thank you for your attention, and don't hesitate if you have any question, I will stay there. Okay? Thank you.